here we have practiced last time. In the last lecture hours, we have practiced this example, and we have practiced the plane of the symmetry for this plane, that is x3 equal to 0. Corresponding to this one, then we knock out the elements. The 0 elements are here. Let me highlight. This one 0, this one 0, 0, 0, 0, 0, and this 0, this 0. Okay. And using the example we just practiced here, the plane of the symmetry is x1 equal to 0. Then the elements we get 0 are those corresponding to their this one. Okay, and the remaining symmetric I leave that alone. Okay, and now we proceed the exercise for this one, and we further simplify this. Okay, so that's a quick, another quick analysis here. X1, X2, and X3. Right now we want to exercise if the plane of the symmetry is X2 equal to 0. Okay. So for this case, any point, this is A, and with the mirror point A prime, this one let me put the X1 coordinate, X2 coordinate, X3 coordinate. A prime, let me put the coordinate x1 prime, x2 prime, and x3 prime. Due to the mirror symmetry in coordinates here, you can tell this is x1 minus x2 and x3. So from here, you can easily build up the table. It's like this. Minus come to here, right? Due to this one. So in a similar way, you repeat this calculation, and we can find tau 1 prime is equal to tau 1 and tau 2 prime equal to tau 2, tau 3 prime equal to tau 3, and tau 2 prime equal to minus tau 2, and tau 1 prime equal to tau 1, and tau 1, prime equal to minus tau 1, Okay, similar patterns apply to string. Then in the similar process, and let me take advantage of the board, and you can utilize the templates, the handouts here, make out the case for yourself. Okay, so right now we have is this, and simply copy that pattern here. So minus is here and here. For string, the same thing, equal to minus is here and here. Okay. So this time, let me try this. So let me try to get the sign of the string into this element. So if you look at this carefully, this matrix expanded representing is the 6 equations. The first equation basically is this element multiplied with this one. Okay, so if once you multiply corresponding this term multiplied with this term multiplied with this, etc. until this term multiplied with this, and that is where minus sign come up with. In this way, you can see we can move the minus sign to here. Every single term, the fourth term under that row will combine with this one, so minus can be moved to here quickly. Okay? In the similar way, for any multiplication of the last element, with this element, the multiplication have a minus sign, I can move the minus sign to the here. Okay? In a similar way, we'll look at this one. So for this equation, once expanded, that is minus 2, 3. And this equation expanding is in this row, multiply with this. write it out. So that is equal to C2311 epsilon 11 plus C2322 plus epsilon 2333. And then here we have a minus sign here already, so put a minus sign here. And C, that is the 23. And then proceed to the fifth term, that is positive, C2313. And six terms, and here that is minus C2312. Okay, so here that is expansion of the fourth equation using the fourth rule in this way. And now we simply move a minus here. So the minus will be this. Come to here, 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 right? And then, oops, this option plus, minus, plus. Hopefully I'm doing it right. Is that right? Supposed to be. Okay, so that means making this term minus, 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 and this one become positive, and minus, positive. Okay. For this term, this in a similar way, this one will be minus, 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 positive, minus, positive. Good. Okay, so now again, right now we have the description of the stress at A related to the strain at A, and that is the stiffness matrix. That matrix must be equal to this content due to the material symmetry. So that means all the corresponding terms must be equal to each other. For example, this element equal to this element, this is a trivial description. A equal to A, nothing new or coming out. For this term, A equal to minus A itself, that means A should be 0. So according to this case, then we can knock out a 0 element should be all the terms corresponding to minus sign here, right? So that means this term will be 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay, etc. So the copy to here, then you use the different color green. So for this one, the plane x equal to 0, that will knock out for that one carefully, that is this one, the 3, and this one, and this one, and this one, and this one, right? Anything else? Do I miss anything? 1, 2, 3, 4, 5, 6, and this, and this. I think that's it. Good? Okay. So far we have successfully applied the exercise for, we call the plane of the symmetry, to exercise how to simplify the contents of the stiffness matrix for describing the material symmetry properties. Okay. Here we can use the result of the three combined operations. We define orthotropy. Orthotropy described is the specific material properties that the material exists three mutually orthogonal plane, mutually orthogonal plane. So orthotropic materials are the materials in which there is three mutually orthogonal plane of the symmetry, just like, for example, x1, x2, x3 plane equal to 0. Okay. And for this case, that depends on the coordinate systems we choose. For example, if you choose the different coordinate systems, say if you choose the coordinate system like this, for example, x1 prime, x2 prime, x3 prime. Okay, if you choose like this, then again, in such a coordinate system, there also exist the three mutually orthogonal plane of symmetry. However, I won't guarantee that plane will be something like, for example, this plane called the x3 prime equal to 0. I won't guarantee whether this plane is a plane of symmetry. There might be the plane of symmetry right now would be, in terms of the new coordinate system, that will be arbitrarily oriented for some reasons, I don't know. But for this case, that is just like our kind of principal direction, we just by chance, that is easy for us to calculate. Okay, so that is a comment on make to you. So here the orthotropic materials are have three mutually orthogonal planes of our elastic okay. So for this case, the contents of the orthogonal materials will be something like this. So this one will be 0, 0, 0. And those four will be 0. And those 5 will be 0. So this is the result after we proceed this kind of calculations. So in terms of contents, here we can calculate how many. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 independent material properties. In the orthogonal material. So for orthogonal materials, we simplify from the very original n-isotropic. N-isotropic has 21 independent elements compared to here 9. So that's much simplified the situation. For to have a material existing in the plane of symmetry, that really require is a certain regular patterns of the arrangement at atom level. So that indicating is this material should be some kind of the crystal line or multi-crystalline kind of the material. Okay, and of course for this material is required is a very strong, very restrictive the plane is they must be mutually orthogonal. That means locally is each plane is in 90 degrees normal to each other. In certain crystal materials, they have a plane of symmetry. They have multiple planes of symmetry, but those planes won't be necessarily 90 degrees to each other. For some crystal material, the plane of the symmetries, the planes of the symmetry, they might be formed is in an angle and make up, for example, 60 degrees or any arbitrary angles. Okay, so for that case, then we can still proceed these kind of calculations. For each simplification applied to one plane of the symmetry, depends on how many planes you'll be able to identify, apply this procedure to each of the planes. Then to see how much you can simplify this to a certain point. Okay. So that is the exercise for an introduction for isotropic materials.